How about going deep, deep into the past to the times before humans existed? Before the infamous asteroid hit Earth, wiping off 3/4 of life forms on the planet. Even before the sun ignited or galaxies appeared in the darkness of the cosmos, so before light could even shine, there was the Big Bang. It happened 13.8 billion years ago. But what was before that? Some scientists are sure that there was no before time. Time started ticking as soon as the Big Bang occurred. We're unlikely to ever figure out what reality was like before that, if any. This is beyond human understanding. But there are those who disagree. Some unconventional scientists theorize that just a moment before the Big Bang, all the energy and mass of the then universe could be compacted into an insanely dense but still finite speck. Let's imagine it as a seed of a new universe. And this seed, a chunk of essential material compressed and hidden in a protective shell, was created nowhere else but inside a black hole. Black holes spin incredibly fast, probably close to the speed of light. Such a spin can give the tightly compacted seed a ginormous amount of torsion. So the seed isn't just tiny and extra heavy, it's also compressed and twisted, which means that it can suddenly unspring with a big bang. Now, let's say you add up the energy and mass of all the particles the visible universe contains, and then you try to figure out the answer to the following question: how big could the event horizon of a black hole with the same mass be? The event horizon is the point of no return. Once you cross this invisible line, there's no way back, even for light. But let's get back to our question. Shockingly, such an event horizon would be very close in size to the actual horizon of the observable universe. There's also this idea that became well known thanks to Stephen Hawking. According to it, every time a black hole appears in our universe, it probably gives rise to a baby universe. But you would only be able to visit such a universe if you crossed the event horizon and plunged inside the black hole. And as you know, once you did it, you wouldn't be able to return. In other words, right now we might be living in a baby universe. But if some outsider is observing us at the moment, our world looks to them like a regular black hole. So, in short, there could be a very old mother universe that forged a seed inside a black hole. This seed had its big bounce all those billions of years ago, and as a result, our universe came into existence. But even though since then it has kept growing and expanding, we might still be hidden behind the event horizon of our home black hole. There's also another idea. According to string theory, there's a multiverse of universes. Imagine our universe as a soap bubble. This bubble keeps expanding, and we live on its surface. String theory claims that our bubble isn't unique, there might be other bubbles out there. And all these bubbles move around, collide, sprout, or bud baby bubbles. In short, they live their life. If we follow this theory, we might suppose that black holes are one-way doors between universes. And if you accidentally tumble down the black hole in our home Milky Way galaxy, you'd end up in another universe. Or rather, not you, but what's left of you after falling through the insane weirdness of the black hole. In this case, this universe wouldn't be inside ours. It would exist separately, and the black hole would merely be the link connecting them, like a shared route between two aspen trees. Whatever the truth, the danger is still there, lurking in the shadows. What if the black hole we live in decides to collapse? What if it pulls us deeper inside? Or, if our world is just a bubble among trillions of other bubbles, what if it bursts one day? A black hole is an eerie place where the laws of physics we studied at school stop working. If a massive star runs out of its fuel, it sometimes becomes super dense and buckles under its own weight, collapsing inward and bringing space-time along. As a result, the gravitational field of this new object gets so strong that nothing can escape it, not even light. That's how a black hole is born. The black holes closest to our planet are called Gaia BH1 and Gaia BH2. They were discovered thanks to the data collected by the European Space Agency's Gaia spacecraft, hence their names. Both are about 9 to 10 times more massive than our Sun and are located a mere 1,560 and 3,800 light-years away, respectively. In cosmic terms, they're situated in Earth's backyard, and there's something seriously wrong about these black holes. So, should you pack your emergency bag? Let's find out. The remarkably close black holes are likely to represent a previously unknown category of these mysterious objects. What sets them apart from others is that they're orbited by stars at much greater distances than scientists have observed previously in other black hole companion star pairings. Normal black hole companion star systems are known as X-ray binaries. They are usually bright in radio and high-energy X-ray emissions. They swallow matter and emit powerful bursts of energy, which makes them pretty easy to spot. Now, why did it take astronomers so long to spot these massive black holes residing right inside our home Milky Way galaxy? All because they're almost invisible. In the past, astronomers spotted black holes by looking for the remnant of their meals. The thing is that when a star or even a cloud of interstellar gas is pulled into a black hole, it leaves behind a trail of electromagnetic radiation, and scientists use it to detect the presence of a black hole. But unlike other holes discovered before, Gaia BH1 and BH2 are pitch black. They don't seem to be snacking on anything at the moment. This makes them inactive or dormant, so astronomers had to use another method. They tracked the movement of two companion stars orbiting these cosmic monsters. The stars, similar to our Sun, wobbled a bit while traveling through space. To researchers, it was a sign that something with a lot of gravity, like another star, was tugging on them. Interestingly, when they examined the area with the help of telescopes, they didn't find anything emitting radiation. So the whole situation only made sense if there was a black hole involved in the process. Luckily, Gaia is perfect for spotting invisible black holes. Thanks to its state-of-the-art equipment, it can accurately measure the motion and position of billions of stars. No other instrument is capable of such precision. Gaia's observations were backed up by the data received later by other observatories. For instance, NASA's Chandra X-ray Observatory, as well as the South African Meerkat Radio Telescope, revealed no visible light coming from Gaia BH2. So even though they detected nothing, it was still valuable information. It told astronomers a lot about the environment around the black hole. A lot of particles are coming towards it from the companion star in the form of stellar wind, but the researchers didn't spot any radio light. It means that the black hole doesn't have much of an appetite, and not many particles cross its event horizon, or the point of no return. Fortunately, it's still unclear why that is. Anyway, should we be worried about those mysterious black holes lurking in the darkness of space so close to our planet? I've got some good news. There's absolutely no reason to worry. First of all, these black holes are sleeping at the moment, and it doesn't look like they're going to wake up anytime soon. Secondly, they're still too far away to affect our life, and it's not like black holes know how to travel. Brace yourself. You're about to hear one of the most unusual sounds ever. It's come from space, and it's the sound of two black holes colliding. But first things first, our ears are designed in a special way that helps us translate sound waves. But these sound waves become mute once the medium they're traveling through comes to an end. It happens when, for example, the atmosphere of Earth gives way to the vastness and emptiness of the cosmos. And at the same time, there are some sound waves that can move even through a vacuum, and we can translate these vacuum-friendly waves into sounds our human ears can hear. That's kind of like how radio transmissions work. Over the past few decades, people have sent quite a few satellites to the far reaches of the solar system and even beyond. These spacecraft are equipped with sensors designed to hear such things as radio and plasma waves flowing freely through interplanetary space. These instruments are crucial for research and communication reasons. An additional bonus is that now we can finally hear different kinds of space waves as audible sounds. The results are often ear-splitting sounds, and sometimes audios are downright scary. Usually, when two black holes collide. They don't produce a sound, but thanks to modern technologies, we can now listen to this terrifying cosmic event. Do you hear it? This chirping sound is the sound that two black holes produced while slamming into each other around 1 billion light-years away from our planet. Interestingly, the tone of the sound rises when the holes spiral closer to each other and stops abruptly when they eventually merge. Now, do you hear that long, low build-up? It means that the merger is quite slow, more sedate, and the black holes taking part in this event are relatively lightweight. A more abrupt chirp is a sign of a fast merger where the black holes are rather large. For example, the pair that produced this sound combined and created one black hole more than 80 times the mass of the Sun. Since each of these black holes weighed as much as several stars, they were hefty enough to produce waves while passing through space, gravitational waves. These are undulations in the fabric of space-time, fanning outward at the speed of light. You can probably compare them to the ripples that appear on the surface of a pond after you throw a rock in the water. Naturally, the sound of black holes colliding isn't the only unusual noise recorded by our equipment. NASA's Juno probe passes by Jupiter every few weeks at a speed of up to 30 miles per hour, plowing through all kinds of invisible fields in the process. One of the most powerful signals it has recorded is Jupiter's bow shock. That's the point where the planet's magnetic field pushes against the incoming wind of solar particles. The sound produced during this standoff sounds similar to a sonic boom. Or this sound, it was produced by the Stardust space probe when it was passing through the dust left by Comet Tempel 1. In the process, debris hit the body of the spacecraft, sounding as if some creature was rapping at the window or hurrying across a hard floor. Let's have a look at NASA's nuclear-powered Cassini spaceship. It spent 13 years exploring the gas giant Saturn and its numerous potentially habitable moons. This mysterious and a bit spooky sound is actually radio waves emitted by the massive planet. Such waves are caused by a phenomenon similar to the one producing auroras on Earth. Speaking of our own planet, it's surrounded by plasma, consisting of hot ionized particles generated by sunlight. They're constantly slamming into Earth's atmosphere. NASA's Polar mission, launched a few decades ago, managed to record this breath-like hiss, which is what plasma orbiting our planet sounds like. As for these weird sounds, NASA doesn't say which space probe recorded them, but they're coming from Jupiter's largest moon, Ganymede. It could have been the Galileo spacecraft, which orbited the system for around 8 years, but it probably doesn't matter so much. Just listen to this creepy noise that sounds like screams trying to break through from some hidden place. Black holes are terrifyingly dense space objects, pulling inside everything that comes too close. Nothing can escape their clutches, not even a beam of light. At the same time, black holes are some of the most mysterious objects in the universe. According to their mass, black holes are usually divided into 3 categories: stellar black holes, which have a mass from a few to hundreds of times the mass of the Sun; intermediate black holes, ranging from 100 to hundreds of thousands of times the Sun's mass; and supermassive black holes, which are the real behemoths of the cosmos, with hundreds of thousands to billions of times the mass of our Sun. Most supermassive black holes lie in the centers of their home galaxies. You could probably say that they sit in the gravitational driving seat, with hundreds of billions of stars, planets, and moons orbiting them. Let's have a look at the biggest black holes astronomers have found so far. NGC 6166 is a monster that has grown to have a mass of 30 billion solar masses. It's actually an elliptical galaxy with an active nucleus in the center. It's also one of the most luminous sources of X-rays. The galaxy's supermassive black hole powers 2 symmetric radio jets in opposite directions, resulting from the infall of gas into its center. Another peculiar thing about NGC 6166 is that it shows a blue shift, meaning it's moving toward us. The next supermassive black hole is located in the constellation of Draco, approximately 10.4 billion light-years from us. The mass of this supergiant is more than 30 billion solar masses. Besides being incredibly massive, the black hole is also really big. If it replaced our Sun, the diameter of this hole would extend into the orbit of Pluto. This S5001 for +81 is one of the most interesting black holes on our list. It has a mass of 40 billion solar masses and is actually a blazar, the most energetic of all quasars, which are super bright distant objects. The blazar's luminosity is 300 trillion times that of the Sun and more than 25,000 times as great as the luminosity of all 100 to 400 billion stars of the Milky Way galaxy combined. But since the distance to this quasar is about 12.1 billion light-years, we can't see it directly, but we know that the central black hole of the quasar consumes huge amounts of matter, about 4,000 solar masses of material every year. IC 1101 is a supergiant elliptical galaxy, the most massive known galaxy so far. Since this galaxy is elliptical, it isn't filled with gas, which is why the star formation in that region is very low. As for the black hole at the center of IC 1101, it has a mass of 40 to 100 billion solar masses and emits clear radio signals. Recently, astronomers have discovered a gravitational space wonder that has swollen to really unimaginable proportions. The black hole I'm talking about is TON 618, a mind-boggling 66 billion solar masses. The thing is so massive that astronomers had to think of a new term to describe it. They came up with an ultramassive black hole. Imagine gathering all the stars in our home Milky Way galaxy and squishing the matter they're made of into one black hole, and it still wouldn't be enough to create TON 618. If this monster of a black hole replaced the Sun, its radius would be more than 40 times the size of Neptune's orbit. You probably know that black holes are made of matter packed together as densely as possible, but that doesn't mean black holes are some kind of space predator, roaming galaxies and munching on everything they come across. TON 618 still has a whole galaxy filled with stars and other stuff happily orbiting it without getting pulled inside. What I want to say is that the perception of black holes as giant vacuum cleaners is wrong. In reality, it's incredibly hard to grow a black hole. Try to do it, and you'll see. Imagine simultaneously being born, growing up, and getting old somewhere out there in the universe. Sounds bizarre and unrealistic, but according to the block universe model of the world, that's exactly what happens with you, me, and other living beings on our planet. It's as if someone drew pictures of every moment of your life and then just piled them one on top of another, creating a giant block of all things that ever happened at any time and in any place. The future, present, and past exist at the same time and are equally real. The block has 4 dimensions, 3 of them are spatial, length, width, and height, and the 4th is time. To make it easier, let's picture our world as a cuboid, which is basically a 3-dimensional rectangle. Its height and width represent 2 of the 3 spatial dimensions of the universe. As for the 3rd spatial dimension, we'll replace it with time. At one end of the cuboid, we'll drop the Big Bang, and at the other, there will be the end of the universe. Let it be a big crunch. Our cuboid is filled with every single event that ever happened, even this moment. When you're watching this video, it exists somewhere in the block. Now, we perceive today as the present, yesterday as the past, and tomorrow as the future. From this perspective, it seems that time passes, but in the block universe, time doesn't flow. There's no specific present moment since the notions of the past and future are relative. You see, we are always located wherever we are, which means that everyone remains in the present. However, the block universe theory doesn't deny the notions of earlier than and later than. These relations remain no matter what, and regardless of where anyone is located. For example, Molly the mammoth is located earlier than Marcus the tiger. This relation between Molly and Marcus will remain unchanged, regardless of whether you're located later than Marcus or earlier than Molly. This way, in the block universe, now is any time you are located at, past is any time or events that are earlier than your location, and future is any time or events that are later than your location. It sounds like in the block universe, we could travel in time since it's just another dimension. Well, it could be true, but of course, things just have to be more complicated than that. Traveling in time is way more difficult than traveling in space, but it's not impossible. If you travel very, very fast, traveling at extremely high speeds results in time dilation. We can travel into the future at a reasonable percentage of the speed of light, and to get to the past, we can use wormholes, shortcuts through space-time. But if we can travel in time in the block universe, can we change the past? Not really, because if you do, it'll create a contradiction. Keep in mind that in this universe, the past is the same as the present or the future. What is past to you is future to someone else, and when traveling to the past, you're going to someone else's future. In the past, you'll act just like you do in the present, but you won't be changing the past. All your actions are already predetermined in the block universe. At the moment of the Big Bang, it's already clear that at one point, you'll travel to the relative past. Just like what you do tomorrow makes tomorrow the way it is and has always been, what you do in the past makes it the way it is and has always been. The events in the block universe do not change. As a time traveler, you don't suddenly appear in the past. It's always been the case that you're located in the past, and nothing a time traveler does can change anything in the block. Instead, whatever you do at any time makes that time the way it is. The universe is believed to have started around 14 billion years ago with the Big Bang, and as far as we know, it hasn't stopped expanding since then. But if it's so, the universe must have started somewhere, right? And there has to be the center of the universe somewhere out there. Well, experts claim there's no center of the universe, neither is there any center of the expansion. It's the same everywhere. You see, it's wrong to imagine the Big Bang as an ordinary explosion, and the universe does not expand from the center outward. Instead, as far as we know, the universe is expanding equally in all places. In 1929, Edwin Hubble said he had managed to measure the speed of galaxies that were located at different distances from Earth. He discovered that the farther they were, the faster they were moving away from us. Does it mean we are at the center of the expanding universe? Unlikely. It just means that the universe is expanding at the same rate everywhere, and wherever you are, it will seem to you that you're at the center of the universe. Now, about that Big Bang. If you watched a regular explosion in slow motion, you'd see material expanding out from a central point. Right after the explosion, the center remains the hottest point. Later, a spherical shell of material starts growing, moving away from the center of the explosion. The process continues until gravity stops this expansion. But the Big Bang was nothing like that. It was an explosion of space, not an explosion in space. According to the most common theory, there was no before to speak of, no space and no time. It means that the Big Bang was very different from anything we're used to and doesn't have any central point. Even if we had been able to observe it in real life, we wouldn't have seen an expanding edge with empty space beyond it. The only thing we can detect now is a faint background glow. It was left by the hot primordial gas that existed in the early universe. This is called cosmic background radiation, and it's uniform in all directions. It can mean only one thing: it's not matter moving outward from one point, but space itself expanding evenly at the same time. The idea that the universe is expanding uniformly in all directions doesn't rule out the possibility that somewhere out there, there's a denser and hotter place that might be called the center of the universe. But as far as we can see, there's no sign of such a special point. The theory that the universe should be uniform is known as the cosmological principle. It appeared in 1933. Not so long before that, some scientists believed that the universe only consisted of our home galaxy. If this was the case, we could definitely consider the center of the Milky Way to be the center of the universe. But in 1924, Hubble put an end to that debate. He showed there were other galaxies besides our own. But in any case, how we see the universe is limited by the speed of light and the finite time since the Big Bang occurred. Even though the observable part of the universe is very large, it's likely tiny in comparison to the entire universe, which may be infinite. The universe might have many shapes, with or without an identifiable center. And if it turned out to have a center outside of the observable universe, this point or region of space could be just one of many. It could be just like the center of our galaxy, which was considered to be the center of the universe before. If you somehow fell into a black hole, it might change your future and erase your past, well, at least theoretically. Let's start with the real world we live in here on planet Earth. Your past can definitely define your future. But imagine you're not on Earth, but somewhere out there in the endless universe, and you stumble upon a certain type of black hole, the one that a UC Berkeley mathematician found. Not to mix it with a regular black hole, let's call this type, what about a benign black hole, huh? So, here's why you need a specific black hole. The thing is, you're highly unlikely to stay alive in a regular black hole. But according to some calculations made by a postdoctoral fellow from UC Berkeley, the specific type of black holes we agreed to call B1s might expand at an accelerating rate. This is what makes it possible to survive the transition from our deterministic world to a black hole, which is not deterministic. Let's imagine you survived that passage, and now you're moving towards the center of a benign black hole. It's impossible to picture what's inside, and if you, as a traveler, could actually get into a black hole, you'd never be able to communicate to the outer world what interesting things are hidden in it. But it's not what interests us for now. We need to know how to get rid of the past. Hence, the mathematician you already know studies non-rotating black holes that have an electric charge. The most important thing about them is that, besides the event horizon, they also have the Cauchy horizon. And here's the point, the Cauchy horizon is the place where so-called determinism simply breaks down. This may sound too scientific, but let me explain it to you. The Cauchy horizon is the place where your past doesn't determine your future any longer. So, here's a mathematically proven and apparently working method of how to get rid of your past. All you need to do is get into space, find a specific black hole, make it to the center, and get to the Cauchy horizon. However, if it sounds too complicated, you can simply try not to make mistakes here on Earth. Yeah, ideas like your past gets cancelled, you have an infinite amount of options for how your future will evolve, and all that jazz sound as unrealistic as they are appealing. Like, imagine no one knows you failed to get into college and get a degree, but from now on, you have every opportunity to do whatever you want. But only theoretically. In reality, once you get into the black hole, not that specific one we've already talked about, you're most likely to disappear once and for all. But hey, don't be sad. I'm only talking about your current physical form. It's a bit deeper than it might seem. The thing is, there's a curious principle of quantum mechanics that can be explained in a simple way. For starters, imagine that you're not a human being but just information. You have your experience, your background, and your thoughts. All of these are the information you are. Now, let's make it even simpler, imagine a USB drive or a book. Both of these things contain information. If you smash a USB drive that contains music and movies, it won't exist anymore in its physical form. The information contained within a USB drive or a book never truly ceases to exist, even if the physical form is destroyed. If you smash a USB drive that contains music and movies, the drive itself may no longer exist, but the information it held persists in some other form. The same principle applies to a book. If you burn it, the physical object is destroyed, but the information contained within it continues to exist in another form. This concept ties into a theory that suggests that even when someone crosses the event horizon of a black hole, a point of no return before being spaghettified, they don't entirely stop existing. Instead, these universe travelers continue to exist, but as information. According to Stephen Hawking, black holes emit radiation, which causes them to shrink over time. Eventually, a black hole might shrink so much that it disappears entirely. So, what happens to the astronaut who got caught in a black hole if it eventually disappears? While they won't be ejected in their original form, they may still be emitted from the black hole as Hawking radiation. However, it's essential to remember that these ideas are just theories, as no one knows exactly what happens inside a black hole. Another theory proposes that what occurs in a black hole doesn't necessarily stay there. Some scientists believe that a black hole might contain a portal where one could potentially turn back time. According to this theory, a white hole exists at the end of a black hole. If you reach this white hole, you could undo events, for example, breaking your mom's favorite vase. By entering the white hole, the vase could be restored to its original state. Similarly, if you cooked scrambled eggs and made fresh orange juice but lost your appetite, a white hole could undo the cooking process, making the eggs unbroken and the oranges whole again, thus eliminating food waste. The idea of turning back time sounds intriguing, and one might wonder if we actually need a black hole to achieve it. If a black hole were created in a laboratory setting, it could potentially grow large enough to consume the entire planet, starting with the Large Hadron Collider, where it might be created, then Geneva, Switzerland, and eventually the whole of Europe and beyond. However, it's more likely that a microscopic black hole, if it appeared, would be so small that it wouldn't pose any real threat. Black holes emit a lot of energy, often as heat, meaning they will eventually fade away when they run out of fuel. Even if a stable microscopic black hole were created, it would grow so slowly that it wouldn't cause any significant harm, and it could take an incredibly long time to gain even a pound of weight. While I won't be around to see it, a black hole on Earth could potentially be a great energy source. Even a relatively small one might emit enough energy to power humanity entirely. Speaking of energy, the concept of spaghettification comes into play when discussing black holes. Spaghettification occurs due to the intense gravitational forces of a black hole, which can stretch objects, including humans, into long, thin shapes, much like stretching a piece of chewing gum. Gravity holds you tightly on one side, causing you to stretch in the direction of the gravitational pull. You might wonder why this doesn't happen on Earth, but the gravitational forces at play in a black hole are far more extreme than anything we experience on our planet.